So the electric field, and I'm going to put when we start these lectures next to the title, I'm going to start putting these objective numbers, and I have the sheet up on Google Classroom somewhere that has the full list of objectives you'll need for the test, and I'll show you that where that is afterwards. But this is objective A.2 from 1 to 4, and you'll see what that means. Okay, so the electric field. So we know the electric force works because charges create an electric field. Which exerts a force on any other charges placed in it.
Mr. Marcus, Harris is in the waiting room.
Yeah, thanks. So the electric field at a point, is given by the force per unit charge on a test charge placed at that point. So it's the force per unit charge on a test charge placed at that point. The equation related to of that statement is the electric field is just the force divided by Q naught, where Q naught is the charge of a test charge. So what would the units be?
Newton something. I forget what the units were.
Is it like Coulomb? Or no, it's like Newton coulombs.
Look at the equation. What are the units of force?
Newton.
Newton coulombs, right?
Newton coulombs.
So we have a force divided by
Charge.
Newtons over coulombs.
Newtons over coulombs, right? Newtons
Yeah, my bad.
Force, charge, coulombs are the unit for charge. So the units for the electric field is just going to be newtons per coulomb. You can always figure out what the units of something is going to be just by looking at the equation.
Would that be micronewtons per coulomb, or just newtons per coulomb?
It could be the SI unit of force is newtons, so the SI unit of the electric field is newtons per coulomb. But another unit of electric field would be micronewtons per coulomb. That could also that's a great unit as well. But
Thank you.
SI. Yeah. All right. So if your force was in micronewtons and your charge was in coulombs, then you would have, if you didn't convert anything, you'd get an electric field in micronewtons per coulomb, and that's great. That's fine. So we need to remember that the electric field is a vector field. Which is a mathematical object that has a vector value at every point. every point in space and even time. So the electric field is really a function of the r vector, the position vector, as well as of time. Although we're not going to be looking at the time dependence until the very, very end of the course. And like I mentioned in the big picture overview for the class, we want to remember that the electric field affects charges, and the charges it affects we call test charges. And it's also produced by charges. And we call the charges that are producing it source charges. And the affecting test charges part of it, that's the easy part. That's just the electric force on a test charge is that test charge times the electric field. Same thing as we defined up here.
Can you bring the page up just a little? Thank you.
I'll give you a minute and then we'll go on to the how it's produced by the source charges. That's the trickier one. But you can see it's not going to be that different since we know how to get the electric force from Coulomb's law. You're going to see it's pretty similar to get the electric field. There's just this factor of the test charge. All right, so it's easy to say how it affects test charges. Easier anyway. But the electric field is also produced by source charges. And that's the part that's a little bit harder. All right. So the first thing we want to look at is the electric field from a single point charge Q at the origin. From one single charge. So if we put a charge Q at the origin, the electric field will tell us, at any point, wherever we put our test charge, what the electric force is going to be. And we know from Coulomb's law, right, if this is our vector, that a test charge Q naught placed at position R, which is some x and y value, or r and theta, would feel a force of K times Q, since that's the source charge, times Q naught, over the magnitude of the distance squared times the, or in the direction of the r unit vector.
Wait, so is that, so it's the electric force equals Coulomb's constant
Yeah,
times Q times the test charge over R squared.
that's right. Times r hat, right? The unit vector.
Yeah, times R.
That's just, and that's just from Coulomb's law. So if we want the electric field from that source charge, which we have already defined as just the electric force divided out with the test charge divided out, right, we can see that that's going to be KQ over R squared, the R hat direction. So it looks a lot like Coulomb's law, except we don't have the test charge. And the idea with this is that the test charge really doesn't matter, right? You can put the test charge anywhere you want, and we can find the electric field at that point. And we can visualize this electric field as well, right? It's always going to be, the vector is always going to be pointing in the R hat direction. So it's always going to be pointing away from the source charge. And the magnitude of it, as R gets bigger, right, it's inverse square law. As R gets bigger, 1 over R squared gets much, much smaller. So as we get farther away, the vector field is going to be weaker. So the way we visualize that is by drawing the arrows farther away from the origin are shorter. And we have some in all directions. When we draw a vector field, right, it's important to remember that there's a vector field line at every point in space, but we obviously can't draw infinite arrows. So we draw, a selection. I'm going to take a second here. There's a few good ways to visualize electric fields. So here's another one. And this one is from academo.org, and I'll put this link up as well. So you can, this one will give you the electric field of up to 2 charges. Right now I have just 1 charge here, 1 positive charge. Right now it's a charge of 2, but we can make it a charge of 1 or a charge of anything. And you can see that the electric field lines point away from that positive charge. Sometimes when you visualize electric field lines, you can tell the strength of the electric field by how closely packed together the lines are. So you can see that near the charge itself here, the lines are pretty close together. That indicates a strong field. But when we look out here, far away from the charge, the lines are spaced farther apart, and that indicates a weaker field. All right. So then, so that's the electric field from one single point charge. And we can find the electric field from more than one point charge by using the superposition principle. And we've already learned what the superposition principle says. It just says we add up the electric field from each of the charges. So the electric field is going to be the sum. If we have I charges of K times the ith charge over Ri squared times Ri hat. And we'll see, we're going to use that in an example in just 1 second. And so if there's two choices, if there's two charges, source charges, then it'll be a sum with two terms. If there's 100 source charges, it'll be a sum with 100 terms. I've got two examples to do, but we're just going to do one of them today. What's that? What's the question?
But what's the thing under the sigma?
That's the index, so the I, right? So I would be the number of charges.
I see. Thank you. So I think we'll just get to the first of the two examples today. And we're going to do the second one tomorrow. So in this one, we're going to look at a dipole. Actually, in both examples, we're going to look at a dipole, which is a positive charge near a negative charge. So we're going to have a source charge Q here, a distance A from the origin, and then another charge minus Q, also a distance A from the origin. And we want to find out some distance over here, some distance along the x-axis, some x value at point P. What is the electric field at point P? The distance x from the center of the pictured dipole. Right, so basically what we're asking is if we place a test charge over here at point P, what's the force going to be on that charge? If we look real quick before we start this at an image again, right? What this would represent would be a charge of +1 near a charge of -1, and both of them would have the same. Oops. So the electric field of these two charges is going to look something like this, right? And it's pretty. It looks a little bit complicated at first, but what we're looking for is what the electric field is over here at this point P, over here to the right. And there's not an arrow drawn right there, but you can see that if the vector at this point was drawn in, it's probably going to be pointing to the left. So we're going to expect, at least from this image, an electric field in the negative I-hat direction. Let's see if that's what we get. Okay, so we have to use the superposition principle, right? So the electric field that we're looking for at point P is going to be the electric field that the positive Q charge makes plus the electric field that the negative Q charge makes. Right. The positive Q charge is going to tend to repel a positive charge placed at point P, so that's going to make an electric field to the right there. But the negative Q charge is going to tend to attract a positive charge placed at point P, so that's going to make the electric field there to the left. And since the negative charge is a little bit closer to point P than the positive charge, that's going to win out, and we should see an electric field to the left. So let's figure out what each of these are. The electric field from the positive Q, if we go back up to our electric field formula again, that's K times positive Q over our distance squared. What is the distance from the positive Q charge to our point P?
A plus X.
A plus X, right? Or X plus A.
I have another question, Mr. Marcus.
Yeah, go ahead.
So if P if P like does not have a negative sign, does that mean it's a positive charge?
So the P is just a point, right? This is where if we were to place a test charge here, what would the charge of the force feel? If the electric, and I've said the electric field is probably going to point, I'm predicting the electric field is going to point into the left. So that means a positive charge placed at point P would move to the left, but a negative charge would move in the opposite direction to the right. Right, so a positive charge will follow the electric field lines, will move in the direction, will be forced in the direction of the electric field arrows. The negative charge will always feel an opposite force, so it'll move in the opposite direction to the way the arrow goes.
So our force calculation assumes that's a positive test charge?
It doesn't assume that, right? Because we divide the test charge out of the equation altogether.
Oh, right, yeah.
Right. So you can think of it as if we put a positive charge there, it'll move along the arrow. If you put a negative charge there, it would move against the arrow.
I see.
The idea with the electric field is that we don't even need the test charge. We're just saying this is the electric field here, so we can tell what's going to happen if we do put a test charge there. And there's one more piece that we need to go here. We need the r hat vector. So if I draw the vector from the source charge to the point P, what direction is that?
Positive I.
Yeah.
Right, positive I hat, right? Because we're going to the right. Is everybody okay with that? How we got, that's going to be just the electric field. So if this was the only charge, right, that would be our electric field here at point.
Okay, so you said we're only going to do one of these examples?
Yeah, I have two. We'll do another one tomorrow.
Okay, okay.
We've got the other one, the electric field from the negative Q charge. That's going to be K times, this time it's negative Q. And what's the distance from our negative charge to point P?
X minus A.
Yeah, X minus A, right? If this distance is X, this distance here is X minus A. So in the denominator, I have X minus A squared. And now I need the r hat, or the direction from the source charge again to the point.
Positive I hat. Oh, wait, from the what? Say that again?
Just the direction from the source charge to the point.
Yeah, so positive I hat.
Right.
Let's go to the right.
Yep, because it's to the right. Right. The fact that this charge is negative already comes into play with this minus sign. Right? We don't need it. We don't have another minus. Good. Questions about that? How we got the electric field from the minus Q? So that means when I add them together, right? I literally just have to add them together. I would get, well, I can factor out a KQ and an I hat. So I'll get KQ, I'll put the I hat at the end. Let's put the unit vector at the end. So this is going to be times 1 over X plus A squared. And since that one's negative, it's going to be minus 1 over X minus A squared. And we can't really stop there. This can be simplified. But this, we've kind of done the physics part now. Now we just have to do the math to get this into a more reasonable form. So we want to make these have a common denominator, right? So if I multiply this term by x minus a squared over x minus a squared, and this term by x plus a squared over x plus a squared. I'll have a common denominator. So I have so I have that minus x plus a squared over x plus a squared times x minus a squared. All right. We're almost there, a little bit more algebra to do. So now I want to figure out what am I going to get when I multiply out this denominator here. So let me take a moment to do that. If I want to know what x plus a squared times x minus a squared, well, that's x plus a times x plus a times x minus a times x minus a. And I know that if I do an x plus a times an x minus a, well, you guys probably have done this more recently than I have. That's a simpler form, right? What's x plus a times x minus a?
X squared. Wait, I don't want to mess this up in it.
X squared
That's x squared minus a squared.
Yeah.
A.
Yeah, that's right. And we have that twice, right? We have an x plus a times x minus
Yeah.
a. That's x squared minus a squared, and another x plus a times x minus a means we can square that, right? So x plus a squared times x minus a squared is x squared minus a squared, the quantity squared. Okay? I think that's right. And the other thing, the other piece that needs to be simplified, if we look at the x minus a quantity squared minus the x plus a quantity squared, that can be simplified. Because if we do that, well, if we multiply this one out, we get x squared plus a squared minus 2ax or xa. And then we're subtracting this one, which is x plus a squared, so that we would get x squared plus a squared plus 2ax. Right? I think that's all good.
Where did you get the 2?
So it's negative
Oh,
4a.
my bad. Yeah.
Yeah, I got the 2 because if I do
I saw.
from
sorry.
doing right, if I do x plus a times x plus a, that's the terms on the left are x squared plus the terms on the right are a squared, and then I have a plus ax and another plus ax from the inside and outside terms. That's how I got this and that from there. And then I'm not sure who said it, but somebody said it, that works out to be negative 4ax. Right, because x squared minus x squared, those cancel. A squared minus a squared, those cancel. And then we have negative 2ax minus another 2ax, because it's negative 4ax. So now we can write this in a much more simplified form. So I forgot the I had over there. That's going to be KQ times, well, we know the x minus a quantity squared minus x plus a quantity squared. That's what we said is the negative 4ax. And in the denominator, we just have the x squared minus a squared quantity squared. And the I hat. So I'll write that just one more time. What we really have there is negative 4 k q a x over x squared minus a squared squared I hat would be the electric field of that. So a lot of this example was math, right? You're basically done with the physics part of it once you figure out what the electric field from the positive charge and the electric field from the negative charge is, and the rest was just kind of algebra, getting it into a simplified form. And as far as I'm concerned in this class, you know, making a mistake in the algebra part of it later on isn't nearly as important as having getting the physics part of it, getting the right equations down to start. So I'm not gonna keep going with this lecture today. There's one more example, which is, and both of these examples are in the third way and do it, by the way. The example we're gonna look at tomorrow is this same source charge here, but the dipole, the point P, is gonna be on the y-axis, so somewhere up here, instead of over here to the right, which is gonna give us a different answer. So this should be enough to get you at least going to make a good educated attempt at the homework problems. Again, if you don't get the homework problems right or complete before tomorrow, that's fine, but you should try to write down where you're getting stuck, what you're getting stuck on. Try to understand if it's the physics or the math afterwards that you're getting stuck on. Are there any other questions on this lecture, this example?